So first, let's review some of the basic definitions and observations of what active galactic nuclei are. This is a picture from Hubble Space Telescope. The bright star-like object is a quasar, and you can see there is some mess going around, and that's because it's fueled by the galaxy collisions, which turns out to be a very common thing. So just as a definition, they're very energetic phenomena in the nuclei of galaxies, and we're now pretty sure that they're powered by an accretion to supermassive black holes that form there, in the same way that we release energy from material falling onto the stellar mass black holes, but here at a much larger scale. And their existence has been gradually realized through the 20th century, but really only began in 1960s. And different classification schemes have been adopted, just like for galaxies. Hubble first came with morphological classification. So active nuclei have been classified according to their appearance, or mostly their spectra. But more recently, people began to realize it's really just one underlying phenomenon with several different flavors, and that we look at them from different angles, and that's what can account for many of the observed differences between them. One important thing is that they evolve strongly in time. There are many more past than there are here now, and that is because their evolution tends to track that of galaxy evolution, and there is actually real connection there. So if you look carefully at galaxies in the nearby universe, you find that at least 1/3 show some sort of activity in the nucleus. And only 1% really are traditionally classified as active galaxies, but if you really look deep down, we think that every galaxy at some point has had some sort of quasar-like activity, and this is where these black holes come from. Now, quasars are the most luminous of them, and in this neck of the woods, maybe one galaxy in a million houses a quasar, but they were 1,000 times more numerous when merging of galaxies was at its peak. So this is sort of artist's conception what the structure of an active galactic nucleus, or AGN, as we call it, looks like. In the middle, there is a small black hole, colored appropriately, and it's surrounded by an accretion disk, which is where energy comes from release of the binding energy of stuff that falls in. This is where most of the emission comes from. There are a lot of gas clouds flying around. We'll talk about that in a sec. But then the whole thing is surrounded by a torus or maybe warp disk of dusty material, which can hide what's happening in the middle if you're looking from the side. That's part of the whole unification scheme. And then some of them, not all, have jets emanating from the middle. They're orthogonal to the accretion disk, and they come from magnetic field that's threaded through the disk or through the black hole itself and accelerate particles to relativistic speeds. So this simple picture can pretty much account for just about everything that we observe. And what we observe are several different things. First, which is very interesting, that unlike stars, they emit energy over a very broad range of energies, from radio to gamma rays. And therefore, if you say pick middle somewhere invisible, they'll be having ultraviolet and X-ray access. They also have radio access, but that's just because their colors and energy distribution is very different from that of the stars. They have strong emission lines because there is a lot of ionizing radiation present that ionizes the gas that powers the line emission. They can be very luminous, up to 1,000 times or 10,000 times luminosities of galaxies. And all that luminosity comes from a tiny region that's smaller than the solar system, way smaller, like within radius of Earth's orbit, roughly speaking, which is what made them so interesting. They're also variable on all different scales because accretion varies and so on. And that right away tells you that that inner region is very small. See, the time it takes light to come from sun to Earth, or one astronomical unit, is a little over 8 minutes. And so quasars have been seen to vary on scales of hours, if not minutes. because their central engine is so small on distances of many megaparsecs or gigaparsecs, they're completely unresolved. They're point sources, just like stars. And that's where the name came from, the quasi-stellar radio sources. Not all of them radio, but that's what it meant. And because they're far away, we can't see them move on the sky. We can observe proper motions of stars in our galaxy, at least near us, gradually over years, but these are so far away that tangential motions are completely undetectable. So each of these properties has been turned around to be used as a method to find them in comparison to other things like stars. And so here is the schematic outline of what a very broad range of spectral energy distributions might look like. The log axis, these are log axes in frequency and in energy per unit logarithmic interval. And it looks pretty flat. Now, stars have more or less black body spectra, and in a black body curve, you come to the half power width of maybe a factor of 2 in frequency, not many orders of magnitude. So a black body of any temperature would be like a very peaked little curve up here. And this is what their optical spectra look like. Well, optical in ultraviolet. There is a very blue continuum. On top of that, there are very strong emission lines. Many of them are very broad, suggesting motions of thousands of kilometers per second in the rest frame of the object itself. Some are narrow, like a few hundred kilometers per second. And then in far ultraviolet, it cuts off, and that's because hydrogen absorbs very effectively everything that's fluid of, say, Lyman continuum limit of 912 angstroms. In many cases, also Lyman alpha line at 1216 angstroms. And when you ask how many are there on the sky, well, you count them. You count them as a function of magnitude, just like we did galaxy counts. And a good reasonable number to remember is down to some sensible flux limits, like 20-some magnitudes. There are approximately 100 of them per square degree. And there are 40,000 square degrees on the sky. So that tells you that roughly there is about some tens of millions over the entire sky down to the detectable limits that we have with our technologies today. Only about 1 or 2 million have been actually cataloged, but we think we could find the others if we wanted to. And there are many more galaxies, so roughly speaking, there is one quasar for every 1,000 galaxies, which is integrated over the entire sky. So what about classification? The first active nuclei were actually seen in the optical, but nobody really understood that this is something special going on. And they really attracted attention with the advent of radio astronomy, where some mysterious cosmic radio sources turn out to be these objects. And so then naturally people divide them in radio quiet and radio loud. If they're radio quiet, doesn't mean they're radio silent. It can be just a very low power radio. And there is probably continuum. In the optical spectrum, some of them only have narrow emission lines. You don't see those broad Doppler widened lines. And so those that are called, that have broad lines called Seifert 1s or type 1 AGN, and those with only narrow lines are type 2. We now know that that's difference just in that for type 2s, the region from which broad lines originate is obscured by dust from our line of sight. There is a sequence of luminosities from almost nothing through thousands of times more in the entire galaxy. The really luminous ones are called quasars, less luminous ones are called Seiferts, dwarf Seiferts, and so on. There are some special subtypes. In particular, remember, there are sometimes radio jets moving out at relativistic speeds. Well, if you happen to be looking right down the jet, then you're going to see some other phenomena as well, including strong variability. And those are called blazars, or BLX. They're named after a prototype, a star called BL Lacerti. And in the olden days, stars were given first Greek names, alpha, beta, gamma, and so on. When they ran out of Greek alphabet, they started giving them Roman alphabet names. And double letters were for variable stars. They kind of gave up after that. Now we know stars by the coordinates. And so something that is like A, B, and then constellation name will be a variable star in that constellation. So BL Lacertae was a variable star in constellation of Lacerta. It turned out not to be a star at all. It turned out to be one of these objects. So quasars were actually seen in 1920s, and nobody recognized them as an interesting phenomenon back then. So some of them are also called optically violently variable. So all these things can kind of go on in parallel, right? Now, type Seyfert galaxies are prototype. Those are active nuclei in mostly spiral galaxies. Seyfert ones have spectra just like quasars. These broad lines, usually broad lines are those of permitted transitions or very abundant elements like hydrogen, and bottom lines are very common. Narrow lines can be from those semi-forbidden or forbidden lines, which you may recall are called that way because they could not be reproduced in the lab, but they can be easily reproduced in a near vacuum of interstellar space. So, for example, doubly ionized oxygen, denoted as O and Roman 3, is a very common line in planetary nebulae and star-forming regions as well. But here it's ionized by something other than young stars. And Seyfert 2s, we see a stellar spectra of the galaxy, and then just some of those narrow lines. Now we can tell the difference between those that are ionized by one of these accreting black holes and those that are ionized by star formation from the ratios of lines. Some of these lines require so much photon energy to excite that they're simply not produced by stars. So you need something other than stars to produce the hard ultraviolet radiation needed for them. And accretion to black holes provides that. In radio, if you were to superpose a radio image onto an optical image of a galaxy, you see things like that. A very common phenomenon is double lobe radio sources centered on a galaxy. There is something in the middle of the galaxy that pumps those out. And those were first seen in the 1950s with first radio astronomical observations. Very quickly, people realized that the amount of energy stored in these radio lobes is of the order of 10 to the 60 ergs, and even more, which is an enormous amount of energy. And the question was, where did it come from? So now we think that, that energy came from an active nucleus, from energy of the accretion, some of which is emitted as radiation, some of which is pushed in a mechanical energy of accelerating particles and pumping them out. And so there is optical as well as mechanical luminosity. This is a modern map of one of the prototypical radio sources, Cygnus A. First radio sources were given named constellation and then A, B, C, depending on their brightness. Very quickly they ran out of letters there, so we don't do that anymore. And in this case, there is a bright radionucleus. There is obviously a jet shooting out on both sides. It's brighter on one side because that one side is kind of more pointing towards you, so the speed of the particle boosts the radiation your way, as opposed to the other side. And they encounter gas in the intercluster medium, and then the whole thing kind of goes turbulent. There are hot spots where jets are hitting it. But you can see there's a lot of structure that goes on. So I mentioned that if you happen to be looking right down the jet, then you see what we call blazar. You see a very strong continuum that is boosted by relativistic motions of particles in the jet moving towards you. And when the continuum goes down, then you can see all the rest of the emission lines and what have you. So that is the observed variety of properties. And now we'll see how we actually explain them.